Here is the combined summary of pages 1 and 2 of the research paper. The authors apply the generalized Komar method to Taub-NUT-AdS spacetime in the theory of Einstein gravity plus a cosmological constant. By deriving a generalized closed-2 form, they calculate the total mass and nut charge of the Taub-NUT-AdS spacetime. They then verify that the first law and Smarr relation hold true. The authors also extend their analysis to charged AdS NUT spacetimes in Einstein-Maxwell theory with a cosmological constant, demonstrating that the generalized Komar method is still applicable. Taub-NUT spacetime, a simple solution of general relativity, has remained understudied due to its peculiar spacetime structure, featuring 2 additional Killing horizons associated with a Misner string singularity. Despite the singularity, the spacetime is geodesically complete and can be treated without imposing a periodic condition on the time coordinate. The Taub-NUT spacetime has 2 integration constants, m and n, where n is related to the nut charge, often viewed as a magnetic mass in contrast to the electric mass associated with m. However, the definition of nut charge remains unclear, and previous attempts have introduced additional conserved charges or treated m as the total mass, which can be negative. The authors aim to address these issues by applying the generalized Komar method, which has been successfully used to define and calculate the nut charge and total mass of Taub-NUT spacetime in Einstein gravity theories without a cosmological constant. In this paper, they extend this method to Taub-NUT-AdS spacetime, where they derive a generalized closed Komar form and calculate the thermodynamic quantities, verifying the first law and Smarr relation. Here is the combined summary. The authors consider the Taub-NUT-AdS spacetime in Einstein-Maxwell theory with a cosmological constant. The Lagrangian is given by equation 1, and the Taub-NUT-AdS solution is presented in equation 2, with the metric function f given by equation 3. The temperature and entropy of the black hole are calculated using the standard method, shown in equation 4. The solution has 2 integration constants, the mass parameter m and the nut parameter n. The authors highlight the importance of expressing the Killing vectors in the form of equation 5, which has a smooth limit when n approaches 0 and allows for a thermodynamical potential interpretation. They note that the definitions of the total mass and nut charge of the Taub-NUT-AdS spacetime are not clear, but recent work has provided a definition and calculation method using generalized Komar integration. In the AdS case, the Komar tensor is not closed, and the authors derive an expression for dd-Xi, which is proportional to the cosmological constant. They then construct a closed Komar-like form Q, defined in equation 12, which satisfies the closure condition in equation 13. The authors note that the u, v components of Q cannot be uniquely fixed and require a proper gauge choice to produce a consistent mass. Finally, the authors define the nut charge Qn using equation 14, which involves an integral of the u plus u components over the radial coordinate. This method provides a way to calculate the nut charge and total mass of the Taub-NUT-AdS spacetime, addressing the previously unclear definitions. The integration of u is divergent in the AdS case, requiring a specific choice for u to cancel the divergent term. This choice leads to the calculation of the nut charge and the total mass of the Taub-NUT-AdS spacetime. The mass and nut charge are related, with the mass returning to the Schwarzschild mass when n right pointing arrow 0. The mass can be negative for larger plus due to the minus r2 plus term, but eliminating musing f, r plus equals 0 yields a non-negative mass. The Killing vector and nut potential remain unchanged, and the first law is satisfied. The thermodynamical volume is the same as in previous works, and the first law is generalized to include the cosmological constant as a thermodynamic quantity. The Smarr relation is obtained using the integrability condition, showing that the nut charge and potential do not contribute directly to the Smarr formula. The Gibbs free energy is calculated, consistent with Euclidean action. The method can be generalized to the asymmetric case through a linear coordinate transformation, affecting the nut potential and the distribution of Misner strains. In the context of Einstein-Maxwell gravity theory with a cosmological constant, the paper explores the thermodynamics of dionic Taub-NUT-AdS spacetime. The solution to this spacetime is given by the metric and Maxwell field equations, which include additional integration parameters corresponding to electric and magnetic charges, e.g. The spacetime has an event horizon at r equals r+, with r+ being the largest root of f, r, equals 0. There exist two other killing horizons, and the associated killing vectors are the same as in the neutral case. The NUT potential, temperature, and entropy of the charged NUty spacetime can be obtained through standard methods. The NUT potential remains unchanged, while the temperature and entropy are influenced by the electric and magnetic charges. To derive the thermodynamics, a closed two-form Q is defined using a generalized Komar two-form, which involves the choice of specific functions, u, v, and their generalized counterparts, u, v. The total mass and NUT charge are then calculated using this two-form, leading to expressions that include the effects of electric and magnetic charges. The paper highlights the significance of the cosmological constant in modifying the spacetime geometry and thermodynamics. It also demonstrates how the introduction of electric and magnetic charges further alters these properties, particularly in the context of the first law and the definition of thermodynamic quantities. The choice of u, v, and u, v is crucial for maintaining the closure of Q, and thus, the validity of the derived thermodynamic relations. In the context of the Kerr-Newman-AdS black hole with a Misner string, we derive thermodynamic quantities using the Hamiltonian approach. The mass, entropy, and NUT charge are calculated as m equals m plus n squared, r underscore plus s equals pi, r underscore plus caret 2 plus n squared, and q underscore n equals n, r underscore plus. The electric and magnetic charges, q underscore e and q underscore g, are also obtained through the same strategy, with their respective potentials, phi underscore e and phi underscore g, defined similarly. When the cosmological constant is treated as a thermodynamic variable, the corresponding thermodynamic volume 5 equals 4 pi, 3 r underscore plus caret 3 plus 1 plus 3 n squared, r underscore plus caret 2 is derived, leading to the generalized first law. Delta m equals T delta S plus V delta P plus phi underscore n delta Qn plus phi underscore E delta K plus phi underscore G delta Qg plus phi underscore n delta Qen plus phi underscore Gn delta Qgn. The Smarr relation, m equals 2, TSPV, plus phi underscore EQE plus phi underscore GQG, is also derived from dq equals 0. The free energy G is evaluated through the Euclidean action, resulting in G equals m, 2r underscore plus 3n squared plus r underscore plus caret 2, 2l squared r underscore plus e squared g squared, r underscore plus caret 2n squared, plus 4e gnr underscore plus 2 r underscore plus caret 2 plus n squared, squared. This result is consistent with the newly derived thermodynamic quantities, F equals mts phi underscore nqn phi underscore eqe phi underscore enqen. The first law exhibits electromagnetic duality under E right pointing arrow G, G right pointing arrow E. The method can be easily generalized to asymmetric distributed Misner strings, yielding similar results. The research focuses on the thermodynamics of Taub-NUT-AdS spacetimes, particularly on deriving the NUT charge and total mass using a systematic method. It involves constructing a generalized closed two-form to solve the problem of non-closure in Einstein gravity plus a cosmological constant. The method is applied to both Einstein gravity and Einstein-Maxwell theory with a cosmological constant. The study shows that the first law and Smarr relation are satisfied, and the free energy of the system is calculated, consistent with the Euclidean action. The results have fruitful applications in holography, such as holographic complexity, conductivity, and viscosity. The effect of the NUT charge, together with NUT-induced electric and magnetic charges, in holography is explored. The paper acknowledges useful discussions with Hong Liu and Liang Ma and is supported by NSFC grants number 12,075,166. The research presented on pages 13 and 14 delves into the thermodynamics of various spacetimes, focusing on black holes and their properties. It begins with discussions on the general Smarr relation and the first law of black hole mechanics, highlighting the importance of these concepts in understanding the behavior of black holes. The papers then explore the thermodynamics of dionic black holes, including the Kerr Taub-NUT-AdS black holes, and their properties such as mass, charge, and entropy. The research also touches on the topic of conformal Killing-Yano tensors and their applications in the Plebanski-Demiansky family of solutions. Throughout, the papers emphasize the significance of these studies in advancing our understanding of the universe, particularly in the context of gravity, thermodynamics, and quantum mechanics.